Hey everyone, welcome to another deep dive. This time we're looking at RNNs.
RNNs.
Yeah, you remember those, right?
Oh, yeah.
They're back.
Back again.
This paper is even asking, were RNNs all we needed?
It's a pretty bold question, right? I mean, for a while there, it seemed like transformers were going to be the be-all and end-all of AI, you know?
Right,
But,
totally.
but the more we learn, the more it seems like different tools for different tasks, right?
Yeah, makes sense.
Yeah.
So for our listeners who haven't been keeping up with all things AI, maybe we need like a quick RNN refresher. What are we even talking about?
Yeah, so basically RNNs, those are your LSTMs, your GRUs, they were designed to work with sequences with data that unfolds over time, right? Like
Okay.
think about how a story unfolds over chapters or how a stock price changes day to day.
Makes sense.
RNNs, they were designed to capture those long-range dependencies, those patterns that emerge over time.
Okay, so they're like the memory masters of the AI world.
Exactly. They can remember those crucial details from earlier parts of the data and use them to make sense of what comes later.
But I vaguely remember there was a reason why they kind of fell out of favor, right? Something about being slow.
Yeah. There was that small issue of training time LSTMs and GRUs. They relied on this process called backpropagation through time, or BPTT for short.
Issue.
And, well, it wasn't exactly speedy. It was like rereading the entire book every time you wanted to understand a new chapter.
Oof. Yeah, that sounds tedious for a computer, too.
Yeah, it was computationally expensive. Like, you'd need some serious hardware to train these things on large data sets.
And that's where transformers swooped in, right?
Yeah.
Faster, more scalable, the whole package.
Exactly. Transformers, they were like the new kids on the block, and they could handle those massive data sets way faster. They kind of stole the show for a while there.
So what changed? Why are we suddenly talking about RNNs again?
Well, these researchers, they figured out a way to revamp LSTMs and GRUs. They found a way to get rid of that pesky BPTT bottleneck.
No more rereading the whole book?
Nope. They came up with a much faster training method, and they're calling these modified models MinLSTM and MinGRU.
Like minimal.
Exactly. They're like the streamlined versions. Not only are they faster, but they also use way fewer parameters.
So fewer parameters, that means like less memory, less processing power needed, right?
You got it. This could be huge for running AI on smaller devices. Like imagine having powerful AI models on your phone or even your smartwatch.
Okay, so not just faster, but also more efficient, potentially accessible to way more people. That's pretty cool.
It's potentially game-changing, democratizing access to AI. That's what I'm talking about.
I'm with you on that one. But let's get down to brass tacks.
Yeah.
How did these revamped RNNs actually perform? Did they just crumble under pressure?
Not at all. They put them through a whole battery of tests, and these min-RNNs, they held their own. One of the tasks was this thing called selective copying, which sounds deceptively simple, but it's actually quite challenging.
Okay, I'm intrigued. Tell me more.
So imagine you have this massive data set, like a mountain of text documents, and you need to find specific pieces of information hidden within all that data.
Yeah, like finding a needle in a haystack.
Exactly. And not just one needle, but like a whole bunch of specific needles scattered throughout this massive haystack.
Okay, yeah, that's not easy.
And a lot of models, even some of the more modern ones, they really struggle with this kind of task. But MinLSTM and MinGRU, they performed incredibly well. They were able to zero in on those crucial bits of information without getting bogged down by all the noise.
Like those super sleuths who can spot the tiniest details that everyone else misses.
Exactly. It was really impressive.
So they can handle long sequences. They're faster than their predecessors, and now they're proving they can extract specific information too. What else did they throw at these min-RNNs?
They also tested them on reinforcement learning tasks, like training AI agents to navigate complex environments, make decisions, and achieve goals.
Oh yeah, like those AI bots that are learning to play video games.
Exactly. And in these tests, too, MinLSTM and MinGRU, they showed some really promising results. They were able to learn and adapt to the tasks, even outperforming some of the baseline models in certain cases.
Wow, talk about a comeback story.
Uh,
But they didn't stop there, did they? What about language modeling? Could they write us a poem?
a poem, maybe not, but they did go head-to-head with some of the top language models out there, including some of the best transformers. And you know what? They held their own.
No way. So they can do it all.
It seems that way. They tested them on predicting the next character in a sequence, which is like a fundamental building block of language modeling, and their performance was right up there with the best of them.
Okay, so now I'm really curious. What did they do to these models to make them so much faster and efficient? I mean, this is like breathing new life into a technology that many thought was outdated.
Right. It is pretty remarkable.
So how'd they do it?
Well, they basically redesigned the way these models handle information over time. See, traditional LSTMs and GRUs, they had this mechanism that constantly looked back at previous steps, like constantly checking your rear view mirror while you're driving.
Okay, I can see how that would slow things down. Always
Yeah.
second-guessing yourself.
Exactly. And it's not just about speed, it's also about efficiency. So these researchers, they found a way to simplify that mechanism. They gave the model a shortcut, a way to process information faster without needing to double check every single step.
So it's less about remembering every single detail and more about understanding the gist of what came before.
You got it. It's like skimming a book instead of reading every single word.
Yeah.
You still get the main idea, the important stuff, without getting bogged down in the minutia.
And they managed to do this without sacrificing the model's accuracy.
That's the amazing part. They found this sweet spot, this balance between speed efficiency and accuracy. It's like they optimized the engine without compromising the car's performance.
So what you're saying is these min-RNNs are like the Teslas of the AI world. Sleek, efficient, and surprisingly powerful.
There you go. That's a great analogy. And you know what else is cool? They found that MinGRU might actually be even easier to train than MinLSTM.
Oh, really? I'm all about easier. What makes MinGRU the low-maintenance friend in this scenario?
Well, it comes down to how they manage information flow. Imagine you're trying to fill a bucket with water, but you've got these two separate faucets, one for adding water and one for draining it.
Okay. Sounds like a recipe for disaster, especially if you're not careful with those faucets.
Exactly. That's kind of what it was like with the traditional LSTM, two sets of parameters to juggle, which could make training a bit tricky. Now, MinGRU is like having a single, well-calibrated faucet. It just simplifies things, makes the whole process smoother and less prone to errors.
So MinGRU is like the Zen master of recurrent neural networks. Streamlined, efficient, and always in control.
Hmm.
I love it. But hold on, we keep talking about speed and efficiency, which are obviously huge. But the paper also mentions something about a smaller memory footprint. What's the significance of that?
That's a game changer, especially as we use AI for more and more demanding tasks. By using fewer parameters, these minimal RNNs require less memory to operate, which means they could potentially run on smaller, more accessible devices.
So instead of needing a supercomputer to run these complex models, we could potentially have them on our phones, maybe even embedded in everyday objects. That opens up a world of possibilities.
Absolutely. Imagine real-time language translation on your phone even without an internet connection, or AI-powered medical devices that can diagnose conditions in remote areas. The potential applications are mind-blowing.
Okay, you've definitely got my attention. But before we get too far ahead of ourselves, I think it would be helpful to ground this discussion in the specifics of the research. Let's talk about the experiments they ran, the other models they compared MinLSTM and MinGRU against, the nitty-gritty details that give this whole thing weight.
You're absolutely right. Understanding the how behind the headlines is crucial. So let's get into it. One of the tests that really stood out to me was the selective copying task.
Right, the whole finding a needle in a haystack challenge.
Exactly. Remember how we talked about those models struggling to extract specific information from a jumbled mess of data? Well, MinLSTM and MinGRU took on that challenge head on and outperformed several other models, some of which were far more complex.
It's like they were tailor-made for this kind of task. What about the reinforcement learning tests? How did they fare against the competition there?
They actually did incredibly well on the reinforcement learning tasks, too. Remember those robotic control scenarios we talked about? They tested MinLSTM and MinGRU on a variety of those, and in many cases, they either matched or exceeded the performance of the baseline models.
So not just book smarts, but practical skills too. These min-RNNs are sounding more and more impressive.
They are. But it's important to note that they didn't completely dominate every single test. While they consistently performed well, there were a few instances, particularly with some of the more advanced decision transformer variants, where other models achieved slightly better results.
Okay, so no perfect score, but still a remarkable performance overall, especially considering they were up against some of the top models in the field. But I have to ask, there was this one part of the paper that went a bit over my head, something about using logarithms in the calculations.
Yeah.
What was that all about?
Ah, yes. That's where it gets a bit technical, but I'll try to explain it in a way that makes sense. You see, when you're working with these recurrent models, you're essentially performing a whole bunch of multiplications in a row. And when you multiply a bunch of numbers together, even tiny errors in those numbers can compound and snowball into much larger errors down the line.
So it's like those rounding errors we learned about in school, but with potentially disastrous consequences for your AI model.
Precisely. To prevent that from happening, the researchers used a clever trick. They performed the calculations in something called log space.
Okay, I have to admit that sounds a bit intimidating.
It might sound complicated, but it's actually a fairly common technique in fields where you're dealing with a lot of multiplications. Essentially, it's a way of transforming the numbers involved to make those multiplications more stable and less prone to those runaway errors.
So it's like putting a safety net under those calculations, making sure they don't veer off course.
Exactly. And the best part is they managed to implement this log space approach without sacrificing the model's performance. In fact, in some cases, it actually improved the accuracy of the models.
Wow, talk about a win-win. But, this whole conversation has got me thinking about the bigger picture. This research isn't just about RNNs. It's about challenging assumptions and being open to the possibility that sometimes the solutions we're looking for might be hiding in plain sight.
I couldn't agree more. It's a reminder that innovation isn't always about chasing the newest, shiniest object. Sometimes it's about revisiting the fundamentals with fresh eyes and asking ourselves, what if?
And on that note, I think it's time to shift gears and explore some of those what-ifs. Because if minimalist TMs and Minjirus can make such a splash, what other outdated technologies might be ripe for a comeback?
It really makes you wonder what else is out there, right? Like, what other breakthroughs are we missing because we've written off older technologies?
Right, like we just assume newer is always better, but maybe that's not always the case.
Exactly. Sometimes the solutions we're looking for are hiding in plain sight. We just need to know where to look.
Totally. But before we spiral down that rabbit hole, let's loop back to those min-RNNs. What other possibilities are they unlocking?
Well, one area where I think they could have a huge impact is edge computing. You see, right now, a lot of AI processing happens in these massive data centers, which can be slow and expensive. But with minimalist TMs and MinJuYus, we could potentially bring that processing power directly to the devices where the data is being generated.
Okay, so instead of sending all your data to the cloud, you could have AI running locally on your phone, your car, even your refrigerator.
Precisely. And that opens up a world of possibilities. Think about it, faster processing, lower latency, more privacy. It could revolutionize everything from personalized healthcare to smart homes to self-driving cars.
That's a future I can definitely get behind. But let's not forget, this research also has implications for the development of AI itself. I mean, we've been so focused on building bigger, more complex models, but maybe there's a different path forward.
I totally agree. This paper is like a breath of fresh air. It reminds us that sometimes simpler is better. By stripping these models down to their essentials, they were able to achieve remarkable results. It really challenges us to rethink our assumptions about what it takes to create truly intelligent machines.
It's like they say the most elegant solutions are often the simplest. So where do we go from here? What are the big unanswered questions, the next frontiers in this research?
Well, one thing I'm really curious about is how these min-RNNs will perform on even more complex tasks. We've seen they can hold their own on language modeling, selective copying, and reinforcement learning, but what about things like image recognition, natural language understanding, or even creative writing?
Now, those would be some impressive sonnets.
Right. It'll also be interesting to see how this research inspires the development of new AI architectures. Maybe there are other forgotten models out there that could be revitalized with a fresh perspective and modern techniques.
It's like we've opened a treasure chest of possibilities. But as we wrap things up, I think it's important to step back and acknowledge the significance of what we've uncovered in this deep dive. We started with a simple question. Were RNNs all we needed? And what we found was a story of innovation perseverance and the enduring power of fundamental ideas.
Absolutely. This paper is a perfect example of how science is never truly finished. There's always something new to discover, always another layer to peel back. And who knows, maybe someday we'll look back on this moment as the start of a whole new era in AI.
An era where the old becomes new again, and where the solutions to our biggest challenges might be found in the most unexpected places. It's been an awesome journey exploring this with you. Thanks for joining us on this deep dive.
My pleasure. Always happy to geek out about AI.
And to all our listeners out there, keep those curiosity engines running, and we'll catch you on the next deep dive.